So I thought I would begin today by doing another couple of examples of integrals over non-rectangular regions. So these are some more examples of doing double integrals for non-rectangular regions. It's an important skill. You'll notice that it's something that's come up on lots of the past exam papers, get it assessed on. So we'll do a few more examples of this, and then there's two main topics left to consider in the multivariable calculus chapter, and that is how to deal with changing coordinate systems in integrals like this. Currently, we've just been doing these integrals using the Cartesian coordinate system, but we're going to be able to also do these integrals in other coordinate systems, in either the polar coordinates or in 3 dimensions, in the 3-dimensional spherical polar coordinates or the cylindrical coordinates and so on. So we want to discuss that. And then there's a last section on Green's theorem, which links together the two types of integrals we've been looking at. These kind of integrals, these double integrals over a 2-dimensional region, and there's a strong link between these and path integrals around the boundary of the region, which we need to talk about. Okay, so those are the two main topics left. But for now, let's look at another couple of examples. So on these ones where we're not actually going to do any integration, we're just going to manipulate the change of order. Okay. So here's the first example. So we want to consider the following integral I. We want to sketch the region of integration and present it using the other ordering. The other ordering of x and y. So here's the integral. At the beginning, we're integrating from 0 to 2 dy, and inside that, we're integrating from y squared to 2y, some function we're not going to be specific about, some function f of xy. Okay. So we got the outer integral is y, going from y equals 0 up to y equals 2, and the inner integral is the integral with respect to x, and this goes from x equals y squared up to x equals 2 times y. Okay. So our first task is to sketch the region. Okay, so it's not immediately obvious what the region of integration is, because you've just got individual limits and so on. I can't see that. Okay, so I'm just going to start sketching the region. So we look at this thing first, and we look at the outer integral. The outer integral goes from y equals 0 to 2. So that means from y equals 0, 1, and 2, the region of integration, whatever it is, must be somewhere in this infinite, or somewhere in this horizontal band. The horizontal band from y equals 0 up to y equals 2. Okay, because that's where we're integrating with respect to the y variable. But then for a typical value of y between these two values, so for a typical value of y, we are integrating from the x variable from y squared up to 2y. So that means there's two boundary curves that are significant here. The two boundary curves x equals y squared and x equals 2 times y. These are the curves that supply the limits of the x variable. So we'll want to plot these. X equals 2 times y is the easiest one to plot first. So it's the line y equals a half of x. So if we have x equal 1, 2, 3, 4, so it's the line x, y equals a half of x. So it goes to the origin on this point 2, 4. Okay, so just that straight line. And then the other curve is x equals the square of y. So if x is the square of y, that means it's going to go through the point 1, 1. And when y is 2x, so it's also going to go through that point. But it's going to be the curve x equals y squared. So this is a curve which comes in like this. And it's going to go through this point and back up here and continue on, something like that. So this is the curve x equals y squared. And this straight line here is x equals 2y. Okay, so once we have these curves, we can start to see what the region of integration is. Okay, because for a typical value y here, in the range of the integral from 0 to 2, we always integrate from starting at the x value y squared, which is going to be the x value lying underneath this point here on the x equals y squared curve. And we integrate x all the way up until we reach the value 2 times y, which is the x value that lies underneath where this line intersects the straight line curve x equals 2 times y. And so at all the intermediate values of y, we have all these horizontal lines, okay? So drawing these horizontal lines between the two curves at every value of y literally shades out the region R, okay? So the region of integration, so I is the double integral over R of this function f of xy dy. Okay, so R is this red shaded region in here. So that was the first task the question asked us to do, and to then change the presentation of the integral by presenting it as an integral where the order has been reversed. So to change the order, we want to write I as a double integral again, as a repeated integral, but this time with y as the inner integral and x as the outer integral. So it still has to be the double integral over this same region, but now we need to change the way it's presented. So x is the outer integral. When you're filling in limits here, when you're working off a sketch of the region or knowledge of the region and constructing the limits of integration, you always work from the outside in, okay? Because the top level operation, what is this thing? Well, basically it's an x integral, okay? Because that's the top level operation. So between what values of x do we have to integrate in order to cover the region? Well, we have to integrate from this value of x all the way up to this value up here. So we have to go from x equals 0 all the way up to 4. Okay, because there are parts of the region at all these x values from 0 up to 4. And what's going on at tip? And remember, it's the outside integral that supplies the values of x to the inner integral. So what limits do we integrate between for the y variable? Well, it depends what the value of x is. The value of x is down here. We're integrating from y. We're integrating along these y values here, which are to the left of this vertical line. But for another value of x up here or something, we're integrating along these vertical values. So the beginning and ending values, the beginning and ending limits of integration for the y variable depend on the value of x. Okay? But they're always the y values, beginning at the y value that lies against the point of intersection between this vertical strip and the straight line, x equals 2y, and ending on the y value of the point of intersection with the curve, x equals y squared. So for a given x value, the lower limit for y, which is on this straight line here, is a half of x. Okay, and the upper limit is going to be the square root of x. Okay. So these expressions come from the two boundary curves, but this time, re-expressing them, making x the subject of them.
You missed the dx after, so I equals at the end.
Oh yeah, just there. Thank you.
Yeah.
That was incomplete. Yeah. Thank you. Okay. So this is how we change the order of integration there. Okay. So these lower and upper limits for the y variable are these lower limit here and this upper limit here. But they themselves are functions of x, because as the value of x changes from 0 up to 4, these beginning and ending values change as well. They rise up. So let's do one more example before we move on to the other topics. So the same tasks for this integral. So we're integrating from a half to 1, but this time with respect to x, and then integrating from y equals x cubed to x, some function dy. Okay. So we want to do two things. We want to find, or we want to see or describe exactly what the region of integration is here, and then change the order around. Okay? Because depending on what the function f is, being able to reverse the order of integration can be useful. It can make the integrations possible to carry out. So we begin with a sketch. Got our x-axis and our y-axis. So the region is contained between the limits x equals a half and x equals 1. Okay, so to space things out a bit. So you got x equals a half and x equals 1. So whatever the region is, it's somewhere in this vertical band. Okay. Then for a typical value in this x region, we're always integrating from the y value x cubed up to the y value x. Okay. So then there's these two boundary curves again. Y equals x cubed and y equals x. Y equals x is easy enough if we've got a half and 1 here for the y variable. This curve y equals x is just simply this straight line. Y equals x. Then we've also got the curve y equals x cubed. And what does that look like? Well, it's kind of coming up here like this. It goes through the origin, and then it kind of curves around. And between 0 and 1, y equals x cubed will be less than x. X cubed is going to be less than x between 0 and 1. But when you go through the point 1, x equals 1, then the y cubed quickly starts to grow very fast. So that's why it's on the other side there. So we can see the region of integration here. So for a typical x variable, for a typical value of the x variable, we're integrating from y equals x cubed up to y equals x. So we're integrating along these y values here. And at the different x values, you trace out the region. Okay, so the region of integration is this shaded region here. It's the region bounded between the two curves, between x equals a half and x equals 1. So R is the region bounded by the curves y equals x cubed, y equals x equals a half, and x equals 1. Okay? These four boundary curves, two vertical straight lines, and then the y equals x line and the y equals x cubed, they capture that region R. So if we want to present the integral the other way around, as a double integral over R of fxy, but this time with the x integral on the inside and the y integral on the outside, well, what do we do? We've got the outer y integral and the inner x integral. Now the y variable, so between what limits of the y variable do we have to integrate to capture the region? Well, there's this, the lowest y can get is this value here, and the highest y can get is equal to 1. And what is this value here on the y variable? Well, it's the y coordinate of this bottom corner point. This bottom corner point is the point on the curve y equals x cubed at x location x equals a half. So this is the y value 1 over 8, okay, the cube of a half. So we have to integrate from all the way from y equals 1/8 up to y equals 1. Okay, you always work from the outside in. And now we think about what the x variable is. So we imagine a typical value of the y variable, and then we look at the starting and ending values for the x variable that go across the region at that particular height. But when we start to think about doing that, we notice something, that there's actually two types of typical y values. For high y values up here, the horizontal strips look like this, beginning on the line y equals x and ending on the curve y equals x cubed. But for lower down y values down here, the horizontal strip is different. It still ends on the curve y equals x cubed, but now for these ones, it's always starting at y equals x equals a half. Okay, we aren't starting over here because this bit over here isn't part of the region. So we actually have two different types of behavior. Okay, sometimes starting at x equals a half, but then once you go through y equals a half, the starting points are then provided by the line y equals x. Okay, so we actually can't achieve this with a single integral like this. Because sometimes we're starting at x equals a half, sometimes we're starting at x equals y. Okay? So the solution is to break it apart. Okay? To break the outer y integral apart so that you've got one integral for one set of behaviors, which is from y equals an eighth up to y equals a half. Then you've got the second integral for the second batch of y values from a half up to 1. Okay, so we go from an eighth up to a half. Plus the integral from a half up to 1, the integral of f dx dy. Gosh. Page slipped. Okay. And now we can determine what these x limits are. Okay. So for the first bit, between y equals an eighth and a half, we're always going from x equals a half up to x equals the cube root of y. So we're going from x equals a half up to y to the power of third. And then for the second half of y values, for y between a half and 1, we're always starting at the x value of y, which is the x value below this point in the curve, and still going up to the x value of the cube root of y. So now we're going from y up to, y cubed. Remember, these y values are between 0 and 1, so the cube root of something, when you're between 0 and 1, the cube root of something is bigger than the y value. Okay. When y is between 0 and 1, the cube root of y is larger than y. Normally, you think a cube root is smaller, but not for numbers between 0 and 1. So that shows you how, again, we've seen this in examples before, but again, how sometimes when you're integrating over the region, if you're using one ordering of the variables might require you to split it up into 2 or more different repeated integrals. Okay, any particular questions about that? Okay. So there are some tutorial exercises there in 1.7 on dealing with integrals over non-rectangular regions and changing the order of integration if necessary. But we're coming on now to study another topic of changing the system of variables that we use, changing coordinates. So this is section 1.17. Changing coordinates. Okay, well, let's jump to the first example, example 2.1. 1.21. And we'll try and we'll see what happens if we we'll see what happens. So what if you were faced with this example? Integrating this function, 1 over x squared plus y squared, integrating this function over this region R. This region R is the region bounded by 2 circles, one of radius A, one of radius B. Just 2 circles. The area bounded by those 2 circles in the top right quadrant of the plane, in the part of the plane where x and y are both positive. Okay, well, how are we going to do this? We'd have to split it up into a y integral on the outside and then an x integral on the inside, 1 over x squared plus y squared, etc. Except the thing to notice about this example is that everything is really circular, okay? The region of integration is a bit between 2 circles. Obviously circular. The function we're trying to integrate involves this x squared plus y squared, which is, of course, the square of the radius, the square of the distance from a point to the origin. The distance from a point to the origin is this radial line from the origin to wherever the point is. Okay? So everything about this looks very circular. Circles are much easier described, much easier described, not in the Cartesian coordinates, but in polar coordinates. R theta. Everybody remember the polar coordinate system is you've got a point here, you specify its location by giving the angle r and the length of the radial line. Okay, so r is the distance from the point to the origin, theta is the angle that the radius line makes with the x-axis, and that's how you locate a point in polar coordinates. How you locate a point in Cartesian coordinates is you give the x-y coordinates of the point. Now you can certainly describe a circle. You can certainly describe a circle of radius a. Here, the formula for the circle of radius a is x squared plus y squared equals a squared. And you can also describe a circle of radius a in the polar coordinates, except it's much easier. Okay. The equation of a circle in polar coordinates is you just specify the value of the radius, r equals this. That's the equation of the circle. The equation of the circle in polar coordinates is much more awkward. It involves both the variables, it involves their squares, and it involves the square of the radius, x squared plus y squared equals a squared. So you've got both variables there, everything is squared. Here you've just got one variable, and there's no function on the variable, it's just specifying the value of the variable. Okay. So circles and bits of circles and so on are quite much easier to describe in the polar coordinates. Okay. So for that reason, we would like to be able to perform. We'd like to be able to perform the integral or evaluate the integral in polar coordinates. Okay, but the question is, given the integral over r 1 over x squared plus y squared dx dy, if we wanted to change it to take place with respect to this new system of coordinates, we need to know how to do it. Okay, well, this is how we do it. It isn't just as simple as putting dr d theta here. We need an extra factor. The extra factor we need is this thing which we studied a few weeks ago, the Jacobian of the transformation from the Cartesian coordinates to the polar, to the new system of coordinates. Not just the Jacobian determinant, but its absolute value. Now, to explain what's going on here, this dx dy expression is often called the area element. And this thing over here is the corresponding area element for polar coordinates. Now, what's going on here? In Cartesian coordinates, if you're at any point in the plane and the x coordinate is changed a bit and the y coordinate is changed a bit, here at this point, if the x coordinate is changed a little bit and the y coordinate is changed a little bit, the area of points that we're describing has area Well, it's just a rectangle. So the area of this point, or the area of this region caused by wobbling the x-coordinate a bit, wobbling the y-coordinate a bit, is just the product of the two, dx dy. That's the area of points we can reach by varying the x-coordinate and varying the y-coordinate. But in polar coordinates, and this is the same thing no matter where the point is. The point is very close to the origin over here, if the point is way up here. If you vary the x-coordinate a little bit, vary the y-coordinate a little bit, the possible points you trace out is just a little rectangle with the original point at its center. Whereas with polar coordinates, something different happens. Let's say we're at this point here, this typical point here, and we vary the radius, r. Well, that will be varying, getting closer to the origin and further away from the origin. And we also vary the polar angle theta. Well, that'll describe a little arc around here. Okay, we're actually talking about these two different radius lines, plus a bit off the angle at this point, minus a bit off the angle at this point. So the actual region we've described here is that area there of that piece. Now that area of possible points that you get by varying r and varying theta, well, if we're this close to the origin, we get a certain range of values. But if we were further away from the origin, if we started off with our base point as being out here, say, and we varied r by the same amount, from varying the radius length, so just coming a little bit closer to the origin, a little bit further away, and varying the polar angle by the same amount, see the area of possible points here, you can easily see is much bigger than this. Yeah? Even though I varied the radius by the same amount and I varied the angle theta by the same amount, okay? The area is different. And you can imagine if the point was like miles away from the origin, okay, varying the radius is still taking, a centimeter step away from the origin, centimeter step towards the origin. But the same variation in the polar angle, if you're located miles away from the origin, that sweep of angles is sweeping out a huge area. Yeah, because the sweep in angles is sweeping out a proportion of the full orbit around the origin. So if you're very far away from the origin, that sweep little change in angle is covering a huge area. Okay? So here we notice that the area depends on the location of the base point. So the area element, due to a change in r and theta, we expect it to depend on the location. It doesn't for Cartesian coordinates. Cartesian coordinates are interesting in that respect. But if you're at some base point and you vary your x-coordinate a little bit, vary your y-coordinate a little bit, you always trace out the same area no matter where you're located. But in polar coordinates, it's different. Okay? Now the actual correct expression there is r dr d theta. Okay, so the area depends on your location simply by the value of the radius for the location of the base point. And in general, if you go from the Cartesian coordinates to any other pair of coordinates s and t, the area element dx dy will always be you take the value of the Jacobian determinant of the transformation from one system of coordinates to the other, And the area element in the other coordinate system will be the product of the differentials, but maybe scaled by this scaling factor here, which is the absolute value of the Jacobian determinant. And remember, the value of, or what dx, dy, ds, dt is, it's this determinant of the matrix of partial derivatives. Okay, so it's this, the Jacobian is an area scaling factor. Okay. It tells you how the area of regions covered by changes in the variables, how that area scales depending on your location. If you're talking about the polar coordinates, it depends on your location simply with this factor of r. And it's true in higher dimensions as well. We'll be seeing, I think in this afternoon's class, we'll look at some three-dimensional examples. Okay. So let's return to example 21. So we have our integral over r, 1 over x squared plus y squared dx dy. Remember, R was this region here between the two circles. The region trapped between the circle of radius, what we call it, A and B. Circles of radius A and B. So, yeah, we want to leap behind the Cartesian coordinate system and now translate everything into the polar coordinates, okay? The function we're integrating is kind of circular because it's 1 over the square of the radius. And the region we're integrating over is circular, so it's a bit caught between two circles. Okay, in a certain quadrant of the plane, but the quadrant of the plane is easy to specify in polar coordinates as well, because it's everything between angle 0 and angle pi over 2. Okay, angle 0 to angle pi over 2 traces out the whole of the top right quadrant of the plane. So it will still be a double integral over the same region. The function we translate into polar coordinates. And then we have the absolute value of the Jacobian dr d theta. Remember, previously we found that the Jacobian dxy dr d theta was equal to r. Okay. The 2 by 2 matrix of partial derivatives is something like r sine theta, cos theta, minus cos theta, or something, r sine theta. So when you do the determinant, it's r cosine squared plus sine squared or something. No, the r, yeah. Right. Yes. The r's are just there. There's no r's there. No r's there. Yeah. But there's r's in the second column, and there's no r's in the first column. So something like cos theta. Anyway, whatever it is. Look back and find it. So this is the thing, and so, well, this looks a bit easier because our 1 over r squared is going to cancel with r, so we'll just be integrating 1 over r dr d theta. And now if we change from this double integral representation into a repeated integral, or a pair of nested integrals, one integral inside the other one. Now, what are the limits of integration? Well, again, you work from the outside in. So you look at your region and you ask, what are the limits for the theta variable? Well, theta is the polar angle. As I said, we're going from angles 0 to pi over 2. Okay. An angle of 0 all the way up to an angle of pi over 2. And for a typical value of theta, So typical value of theta is something in the middle. Between what limits of the other variable are we integrating? Well, the other variable is r. So that question is easy to answer. Between what values of the radius are we integrating to capture the region? Well, we're integrating from radius A up to radius B. So the r integral goes from A to B. So actually, this region R, it really is a rectangle, in quotes, a rectangle in polar coordinates. Okay, it's a region of the plane specified by constant limits on each of the variables. 0 and pi over 2 for the theta angle, and A and B for the radius, whatever A and B happen to be. Okay? So this is what a in quotes rectangle looks like in polar coordinates. A bit of the plane specified by constant limits on the two variables. So we can easily evaluate this. The first thing we can notice is that the inner R integral makes no mention of theta at all. The inner integral has no dependence on the theta, okay? Because whatever the value of theta supplied by the outer integral is, the inner integral completely ignores it. It's just always integrating from r equals a up to b, and there's no thetas mentioned in the function that we're integrating. So this is what's called, what we met previously, we termed a separable example, okay? The function we're integrating is separable. So this thing can actually, by the properties of integration, this can just slide right out of the integral. And it leaves behind 1. Don't write down, it's a factor of 1. So it's just really the r integral multiplied by this. Now when you integrate 1 over r, you get, of course, the natural logarithm of r, evaluated at a and b. And you integrate 0 to pi over 2 d theta, you get pi over 2. Integrating 1 d theta just gives you theta, evaluated at 0 to pi over 2, gives you pi over 2. And well, it will be the difference in values, the natural logarithm of b minus the natural logarithm of a, and all of it multiplied by pi over 2. Or if you want, as it is in the notes, it's turned into the natural logarithm of the quotient b over a multiplied by pi over 2. There's properties of the natural logarithm. A difference of logarithms is the logarithm of the quotient. So the actual integration there was relatively painless. Once we'd done the translation to the new coordinate system, which happened here, there was no particular obstacle posed by the integrals. Whereas if we had tried to do it up here, I'm not saying we wouldn't have been able to do it, but we would have been integrating from y equals 0 up to y equals b. But then the x integral would sometimes have been located starting on the circle, sometimes starting at x equals 0. And the expressions in y, that would be the upper limit for the x variable, would be some expression like the square root of b squared minus y squared. So the limits of integration would have been very much more awkward if we persevered and tried to do it in the Cartesian way. Okay. So staying with the Cartesians makes the integral hard. It's worth trying to do it out just to see how much more difficult it is. You might actually be able, because it's not too crazy, you might actually be able to evaluate the thing out with Cartesian coordinates, but you would probably end up making, in order to do the integration, you would probably end up doing some kind of trigonometric substitution for x and or y. Making some, because one of the methods of integration could be substituting some trigonomic, some new variable defined as a sine or cosine or something of the previous variable, which is in effect changing to the polar coordinates, really. Okay. Okay, so when I see you later on this afternoon, this evening, we'll look at some higher dimensional examples of this.